Hello, I am pleased to be with you again once more. And still you are in the studying the subject of limits. Now, in our last lecture, the task was to prove the existence of the limit. Here, it's not a matter of proving the limit, just to find it. And this is why it's much easier. So to find the limit of a function, you doesn't necessitate that you use this epsilon delta mechanism of the German mathematician Weierstrass. And this is what we actually did. Is to what we explained in our last lecture is that to prove the limit of a function at a certain point is to prove that if any point x that you take in a deleted neighborhood of the point at which you seek to determine the limit of the function, if this x approaches the point a without touching it, of course, and because the function may not be defined at a or not, and this is not the question, if this is so, then at the same time, if f of x approaches a definite value L, of course, in a deleted neighborhood of the value L, then in which case you can say that the limit exists. In other words, you find a relation between delta and epsilon, so that when epsilon tends to 0, delta also tends to 0. Then you can then conclude definitely that since this L is finite and real, then that the limit of the function exists. Now here it's different. Here it's not to prove the limit, just to make sure that the limit exists. So it's much easier task we shall undertake this time. So in this lecture we shall be speaking about the limit theorems. In other words, the limit that we shall use to show or to evaluate limits. First of all, we shall speak about the algebraic laws of finding limits. What about the limit of circular functions? In other words, trigonometric functions, when you have sine, cosine, etc. There are some special rules devoted to these kind of functions. And then you have what's called the squeeze theorem. In books, it's called also the sandwich theorem, according to Lord Sandwich, the one who had introduced, or his wife, the sandwich because he used to go hunting or fishing, etc. So instead of having a full dish, so he usually takes sandwich, and the idea of a sandwich, the same thing, the squeeze theorem. You have two functions approaching a limit, and this in between, so it approaches the same limit. This is called the squeeze theorem. And then you have the number E. We have to investigate number E, because number E, which is called Euler number, this is important because it appears in economics and in many other applications. And then we shall speak of domain function, because functions are like persons. You have a person with a strong personality and one with a weak personality, and the one with a strong personality lead the way. In other words, the other one accepts his terms, and same thing with functions too. Now, the algebraic laws of functions. The algebraic laws of functions resemble very much the algebraic laws of numbers. In other words, when you have, for example, first of all, we start by sequence, because actually what applies to sequence applies to functions. When you have here, for example, two sequences, capital X and capital Y, with elements xn and yn, and there are two convergent sequences. In other words, the limit of xn tends to x, and the limits of yn is equal to y when n tends to infinity. Then you arrive at certain rules or theorems. These are theorems, and they are simple actually to prove. Here you add, for example, the sum of two sequences. Of course, the sum of two sequences is another sequence. So if you are sure that the sum of two sequences, where each sequence you can prove that each sequence is convergent, in other words, tends to a limit, then the sum also tends to a limit, and the limit of the sum is equal to the sum of both limits. Again, when you have the subtraction of two sequences, which is composed of the sequence of terms such that each element of it is equal to the nth element of x minus the nth element of y. Now, since capital X and capital Y are convergent, in other words, the limit of xn tends to certain x and limit yn also tends to certain y, then the limit of x minus y as a sequence will tend to the difference between both limits. And same thing when you have, for example, the product of two limits, the product of two, sequences. When you have, for example, a sequence whose terms is equal to xn times yn, where xn are the elements of sequence x and yn those of another sequence y. So when you multiply the sequence together one by one, you get a sequence capital xy. This sequence, the limit of which will be the product of both limits x, y. And these are, as I said, theorems. Here you don't have to use the epsilon delta mechanism. All you have to do is just you try to find the limit not to prove the existence of such limits. Again, if you multiply a sequence by a constant, then the limit of the sequence, the new sequence, is equal to this constant times the limit of the original sequence. Finally, if you have, for example, the quotient of two sequences, of course, such that the limit of the denominator, the limit of the sequence at the denominator is not equal to 0. Then you have a new sequence. Each term is denoted by xn divided by yn. In other words, the sequence, the element of the first sequence is divided by the corresponding element in the second sequence to obtain a new sequence called capital X over capital Y. So if each of x and y tend to limit small x and small y, then the limit of this new sequence will be is equal to small x over small y. In other words, the ratio between both limits, provided, of course, that the limit of the small y, or the limit of the sequence in the denominator, is not equal to 0. Now, suppose you want to calculate the limit as n tends to infinity of 2n plus 1 over n plus 5. And now 2n plus 1 over n plus 5, this is a sequence defined for all values of n. When n is equal to 1, you get 2 over 6. When n is equal to 2, you get 5 over 7, etc. This is a sequence, and you want to know whether it converges or not, and what is the limit of this sequence. So all you have to do, the best thing of dealing with this sequence, like we said before concerning functions, when we were studying the asymptote, the horizontal asymptote, we used to exclude the the higher order or the higher degree of n. Here, for example, we divide both numerator and denominator by n to obtain a sequence of this sort. Now, you can now distribute, because we said that the limit of x divided by y, the limit of the numerator divided the limit of the denominator, provided that that of the denominator is not equal to 0. And here it's not equal to 0, so that is equal to the limit of the numerator, which is 2 plus the limit, because these are, again, a sum of two sequences, one which is constant all the time. So the limit is 2, the other one, 1 over n, and we proved this before in our last lesson to be equal to 0. So this is 0 and this is 0, and you get at the end 2. So the limit of this sequence is equal to 2. In other words, this sequence approaches the value 2 as n tends to infinity. Now, these are concerning functions. As a matter of fact, there are an analogy between functions and between sequences. What applies here applies there. So here, for example, you have the sum of two functions, and you wish to calculate the limit and x tends to a. Now, at x tends to a, if the limit of each of them is convergent and tends to a certain limit, then the limit of the sum is equal to the sum of the limit. Again, the limit of the product, if both are convergent and tends to a limit of the first one, called Ln, L1, for example, and the other one is L2, so the limit of the product is equal to L1, L2. In other words, the limit of the product, again, is equal to the product of the limit. Again, if you have a quotient of two functions, f and g, the limit when x tends to a is equal to the limit of the numerator divided by the limit of the denominator, and of course, provided that the denominator, the limit, is not equal to 0. Now here, for example, here you have a function like this, and this function has an horizontal asymptote. How would I know this? Because if you take, as we did before, in order to evaluate this limit when x tends to minus infinity or to infinity, same thing, is to extract the higher value, the higher order degree of x. Here you can get x outside the square root. Now, we said before that the square root of x squared is not equal to x, but it's equal to mod x, the absolute value of x. So you get here the absolute value of x times 1 minus 9 divided by 4x squared divided by x. Now, how would I calculate this limit? You have here a limit of two functions. One is modulus x, which is absolute value of x divided by x, and the other one is the square root of 1 minus 9 over 4a squared. Can you distribute the limit? Yes, you do, because the limit is equal when you have a product of two limits. The limit is equal as you apply our last theorem. The limit of a product is equal to the product of the limit, and then it's equal to the limit of the first function times the limit of the second function. Now the second function is easy because the limit when x tends to minus infinity, this tends to 0, so you get 1. So there remain here the limit of modulus x over x. Now modulus x over x, we investigated this function before, and we said this doesn't tends to a limit as x tends to 0. From the right it tends to 1, and from the left it tends to minus 1. But when x tends to infinity, then x modulus x is equal to x because it's positive, so it tends to 1. Whereas from the left hand side, when x tends to minus infinity, then this becomes positive, whereas this becomes negative, so it tends to minus 1. So here, if you are interested in investigating the limit of this function as tends to minus infinity, this becomes negative and this is positive, so it tends to minus 1 times 2, you get minus 2. So the limit, the one that we seek to find, the limit is equal to minus 2. Whereas if you are interested in the limit of this same function, when x tends to infinity, you find equal to 2. In other words, this function has two horizontal asymptotes. One is equal y is equal to minus 2, and one is y is equal to 2. Here the function defined, of course, the function is not defined in the open interval from minus 3 by 2 and 3 by 2. How did I know this? It's easy. Because here 4x squared minus 9, all you have to do is that to set what's inside the square root positive. So if this is positive, implies that x is greater than or equal to 3 by 2 and less than or equal to minus 3 by 2, where in between it does not exist. So this function has a domain union of two closed interval from 3 over 2 till infinity and minus infinity to minus 3 over 2. Whereas it has two horizontal asymptotes. One is y is equal to 2 and y is equal to minus 2. In fact, it should have had a vertical asymptote. Why? Because I have here a root in the denominator x equal to 0. So, but the problem is that with this at x equal to 0, the function is already undefined. Because when I set the numerator, as I said before, you set the denominator equal to 0, but at which the value of the root, at which the numerator is not equal to 0. Of course, in fact, here the numerator is not equal to 0, but it's equal to square root of minus 9, which is not exist. So the point x equal to 0 does not lie in the domain of the function, and therefore this function has no vertical asymptote, but it has two horizontal asymptotes. Again, you have, these are algebraic laws of function. When you have a limit of a function raised to the power n, you can introduce the limit inside the function here. You can say that it's equal to limit f of x as x tend to a to the power n. In other words, you can insert the limit inside the function. And same thing here. This is another way. Here only n is an integer. In here n is not an integer. I'm sorry, I'm just saying that n also is an integer. It could be, but you have f of x to the power 1 over n. So you may have, for example, limit of x squared is equal to limit f all squared, or you may have limit square root of f of x, which is equal to the square root of limit f of x when x tends to a. In other words, you can manipulate the limit inside the function. You have here, in fact, what you have here is a composite function between x to the power n and f of x. And here you have again a composite function of the square root of x and f of x. So when you have a composite function, f of g, what you do, f of g of x, and you investigate the limit of f of g of x when x tends to a, you first investigate the limit of f of g, and then you introduce f to obtain f of limit f of g. For example, this is a situation in which you have a limit here, and it looks complicated, but when you have square roots like this, what you do is that you multiply both numerator and denominator by, for example, the conjugate of the numerator. Here you have minus 4, the square root, so we multiply by minus 4. This is a trick that usually teachers give to the students. You multiply by minus 4 minus 9, both numerator and denominator. Now the numerator, when you multiply both brackets here, you get this, and the denominator here you have h, so this cancels out h with h, and you are left out with this. So here again, when you are left out with this, here you have minus h by h, you have minus 1. In other words, you end up with the square root of limit when h tends to 0 of 1 divided by 4 plus square root of 16 plus h. When h tends to 0, you get square root of 16 is equal to 4. 4 plus 4 is equal to 8, so you get 1 over square root of 8. And here, of course, what we did is that we inserted the limit. We used the previous theorem. We insert the limit inside the square root, which you can always do, provided that the limit inside exists. Now, this is one of the theorem which we use sometimes. The limit of x, you have a quotient x to the power n minus a to the power n divided by x to the power m, where n and m are integers. When x tends to a, you got the theorem, and the proof is simple, as a matter of fact. The proof of this theorem is simple. You can use it directly, and you use it to obtain limits of many functions. For example, here you have a limit of this sort. You want to obtain the limit. What you do, you can actually do a kind of substitution. This is the easiest way of doing it. You take the square root of 1 plus x is equal to y. So this become what? Y cube. This become y cube minus 1. And here x, you have from here 1 plus x is equal to y squared. So x is equal to y squared minus 1. So you end up with this expression. In other words, when you substitute x for y, you have a limit with y. Now you can apply the theorem. You have y to the power n minus 1 divided by y to the power m minus 1. So you get n divided by m, 3 by 2, times the a, which is the point, over 3 to the power 3 minus 2. You get 3 over 2. I mean, these are simple tricks in which you use theorems. So there are really a multitude of theorems which you can use. When you deal with circular functions especially, there are only two theorems which we use. The first one is limit sine x over x when x tends to 0, which is equal to 1, and limit 1 minus cosine x over x when x tends to 0 is equal to 0. And in fact, they are not two, they are one, because you can deduce the second one here from the first one. So, and this is, I can really state that this, in fact, is perhaps the only limit theorem concerning trigonometric functions, because, and this exists all the time. For example, suppose you have 10x over x. The same, limit 10x over x when x tends to 0 is equal to 1, because the 10 is sine over cosine, and cosine when x tends to 0 is equal to 1, so you get the same thing. If you have limit 10x over x to the power 3, so you introduce the limit inside, and you get also 1. So you try to manipulate these theorems, and all the time you find a way to work out your problem based on very simple results, like this one here. And to prove this result here is simple. Why? Because how would you do this? You have, for example, this circle, because you said this is a circular function. You have a circle of radius. You can take the radius is equal, for example, to d. And here you have you have a radius making an angle x with the horizontal. You extend it to the point B, where AB is perpendicular to OA. Now here you can compare between three areas. The first one here, which is the triangle OCA. And then you have the circular sector here, OAC, and then you have the great triangle. Now, the small triangle, the area of which is equal to what? The base times the height divided by 2. Now, the base is D, and the height is equal to what? Is equal to D sine X. So you get half of D times D sine X, and this is the area of the first triangle. So the first triangle here, this small triangle here, it has an area of half D squared times X. Now, this is smaller than the sector, and we know that the area of sectors, the area of a sector making an angle, a radial angle x, is equal to half d square, which is r square, the radius, times x in radian of the same, of the angle of the sector. Whereas the area of the bigger triangle, which is the higher or the greater area of all, is equal to the base times the height. The base is equal to d, whereas the height is equal to what? To the base times 10x, because the height, the opposite divided by the adjacent, is equal to 10. So the opposite becomes equal to d10. So you had d10, which is the height, multiplied by the base, divided by 2, and you get this expression. Now you can take these two together. You cancel out d square, and you cancel out 2 from both to obtain sine x less than 10x. And actually you can get d directly. Why? Because since sine x is less than x, it means that sine x divided by x is less than 1. So you obtain the first inequality on the right-hand side. Whereas from these two inequalities, since x is less than 10x, and 10x is sine x divided by cosine x, so you divide both by sine by x, and you multiply both by cosine x to obtain what? Sine x over x, again, is greater than cosine x. So you end up with this inequality here. And since the right-hand side and both cosine and 1, they tend to 1 and x tends to 0, which means that the one in between sine x over x also tends to 1 as x tends to 0. And this is a simple way of proving this result here. And this result, as I said, is perhaps the only result concerning circular functions. And from there on, you can move to this one here, and you can move to other results concerning limits of circular functions. Now here, for example, this is a circular function, inverse of sine x, but what you can do, you can substitute sine minus 1x. This is not 1 over sine. This is the inverse function of the sine function. So you can set this equal to y. In other words, x is equal to sine y. So by transforming x into y, you end up with this expression here. Again, this you can use the limit of circular functions y, because you can divide both numerator and denominator by y to obtain this. Now you have a limit of 1 divided by sine y over y. And you can use the theorem, the algebraic theorem that we have used before, we have seen before. The limit of f of x over g of x is equal to the limit of the numerator divided by the limit of the denominator. So you get 1 over the limit of sine y over y when y tends to 0. You can distribute the limit in the numerator and denominator, but this is equal to 1 from the preceding theorem. So actually the limit of this function becomes equal to 1. Now this is an important theorem. It's called the squeeze theorem or sandwich theorem, and this exists many times in application. When you have, for example, when you have a police patrol, for example, want to stop a car which exceeds the limit, what it does is that it tries to squeeze this car between the police car, the patrol car, and the end, or you say the trottoir, so that it makes it stop. How do you do this? By just squeezing it. So long as the car, the exceeding or the penalized or the one which exceed the limit always lies between the two, so it must stop eventually. And this is the meaning of the squeeze theorem. You have two functions, and both of them, as a matter of fact, in French, they call the theorem de gendarmerie. And it's funny that I discovered that they have the same feeling, that it's the way you have two things that go together and approach a certain limit, so the one in between must approach the same limit. This is by logic. For example, here, you have f of x and g of x. Both functions, for example, approach this limit at the point x equal a. And if h of x is always in between these two functions, so it must approach the same limits. For example, suppose sometimes you use this theorem to calculate some limits of this sort. A limit of x squared sine over 1 over x squared at x tends to 0. Now, I know that the sine function, the range lies between -1 and 1. So setting up this inequality here, and then you multiply by x squared, you get this. But then x squared and minus x squared both tend to 0 simultaneously. So the one in between must tend to the same limit. And to show this on an applet here of Cairo University, done by the gentleman called Bassem here. Here, for example, this is the example that we showed. Here you have x squared sine 1 over x squared. What you do is that first you have an envelope, x squared and minus x squared. Both tends to 0 at x tends to 0. So the one in between, which is the function we are interested in, must also tend to the same limit, since it's all we are sure that it's in between. Again, here, for example, you have e to the minus x squared cosine x. Now, e to the minus x squared, it looks like this. This is e to the minus x squared, and this is minus e to the minus x squared. So if you multiply by cosine x, then cosine x, since it's equal, less than 1 and greater than -1, multiplying it by a positive quantity makes it less than e to the minus x squared and minus e to the minus x squared, and both they tend to 0 as x tends to infinity. So you said that the function also tends to 0 as x tends to infinity. Finally, when you have sine x over x, the one that we saw before, here it is you have sine x less than 1 and greater than -1. So if you divide by x, then you make it bounded by 1 over mod x and 1 minus 1 over mod x, and both, since both tend to 0 at x tends to infinity, you find that the function also tends to 0 at x tends to infinity. So we often use this sandwich theorem to prove many results in limits of functions. Now, an important result of limit is the exponential function. Here we have the Euler number on your calculator, and Euler number, it's known from the 17th century, but it has been investigated by a person, a Swiss mathematician called Euler. And this Euler number here, you can define in this way. It's a sequence of numbers which converge to the value 2.718, and you can define at the limit of this sequence here. You have 1 plus 1 over n to the power n. In other words, when you take this limit, you find equal to the value e. In other words, when you draw the graph 1 plus 1 over x to the power x, and you keep increasing x, you find that you have an horizontal asymptote y is equal to e. What is interesting here about the number e is that it appears often in interest. For example, when the bank tells you, for example, you can have a deposit and it gives you, for example, an interest on that deposit. Sometimes the bank tells you, why don't you, for example, put your money, for example, only for 6 months. It's called cumulative or compounded interest. Instead of, suppose, for example, you have a 10% interest on your money. You put, for example, 1,000 euro, you get at the end, for example, 1,100. But it tells you, no, you put it only for 6 months. Instead of having 10%, you take only 5%, and then after 6 months, it's compounded, it's cumulative. It's you put it again to get a better interest. So will really this is the case? Actually, we can prove that there is an upper bound. It's not true that because banks are not foolish to let you get more than what you really deserve. So suppose now we take an interesting problem here with the number e, and we calculate an upper bound for the bank interest. So here, what you have a bank which gives you 10% for each euro. If you have 1 euro, at the end of the year you have a 10%. In other words, you have 1.1 euro, and this is the money that you found at the end of the year. But you can also, the bank can also convince you that you may have a cumulative interest. In other words, you get only, instead of 10%, you have 5%. And then after 6 months, you put this money as a new deposit to obtain a better interest of 1 plus 0.05 square. In other words, at the end of the year, instead of having 1.1, in other words, you instead of having an interest only of 10%, you get an interest of 1 plus 0.1 over 2 square minus 1. So it's a little bit higher than 10%. What about if you put it, for example, for 3 months? Then you divide 10% by 4 to the power 4. Each 3 months you accumulate your interest, or you compounded your interest. Would this be higher? Suppose we keep on like this and you put it even for 1 day. If n is equal to 365 days, or you can put it for an hour even. Sometimes the bank tells you, if you put it for an hour, I give you such and such an interest. Then at the end of the year, what you get? You get 1 plus 0.1 over n to the power n. Now, what's the value of this as n goes to infinity? Otherwise, when you number of subdivisions, instead of having 3 months, or instead of having every 1 month, or even for 15 days or 1 day, etc., what is the upper bound that you can get for your interest? It's easy, because here is we can calculate it. You have 1 plus 0.1 over n to the power n, and we want to take the limit when n tends to infinity. So what we do here, we can substitute 0.1 over n is equal to 1 over m, so that you have here 1 plus 1 over m, and you substitute n for what? 0.1 m, and you want to apply the limit as m now tends to infinity. Now this is equal to what? This is equal to, we try to apply the algebraic laws of limits. Here you have what? Here you have limits of 1 plus 1 over m raised to the power m, or raised to the power 0.1, so introduce the limit at m tends to infinity, all to the limit 0.1. But we know that this is equal to what? This is the number e. So at the end, really, you get e to the power 0.1, and this is what is written here. E to the power 0.1, that's the maximum of your money for 1 euro. When you put 1 euro, at the end of the year, you have 1.105. In other words, it's not 10%, it's a little bit more than 10%, it's 10% and a half. So it's not much really when you put your money, even if the number of subdivisions goes to infinity, and you put it even for 1 hour, you never exceed 10.5. And as a matter of fact, the bank is more cunning than you, so it tried to modify multiply the rate so that when you put it for a little amount of time, less than a year, it gives you a little bit smaller profit, so that in the end you never exceed, because otherwise everybody would put his money not for 1 year, but you put it for less number of days, less than 365 days, etc. And even if you keep augmenting the number of subdivisions, same thing, you never exceed 10.5% of your money, provided that you already, the money have announced that they give you 10% interest for your money, for your €1 at the end of the year. This is associated with the number e. You have the exponential function, and we saw this function before. We said that the function e to the power x and logarithm x, those two functions are opposite or inverse to one another. E to the power x, this is a function that grows indefinitely, and this is one of the highest rate, has the higher rate of growth, or the derivative goes to infinity very quickly. You have e to the power x. The limit e to the power x is equal to, this is the definition of e here, which is limit of n tends to infinity of 1 plus over n to the power n. All you have to do, you multiply it by x to obtain the function e to the power x. Now, e to the power x, e to the x, this is a function where when x tends to infinity, it goes to infinity from one side, but when x tends to minus infinity, it attenuates to 0. So this, as a matter of function, is responsible for all phenomena that attenuates or diminishes or decays, or they grow forever. Limit e to the x as x tends to infinity is infinity, and as x tends to minus infinity is equal to 0. Now, what about the logarithm? The logarithm, which is the inverse of this function, the same thing. When x tends to infinity, it goes to infinity. But it goes to infinity slowly, much slower than the function e to the x. E to the x is much stronger. Whereas when x tends to, because the function e to the power x has a domain r and a range, the open interval from 0 to infinity. So since this is the inverse of this function, so this function must have the domain, the open interval from 0 to infinity. In other words, you have to take the limit when x tends to 0 plus, because it's only valid for x greater than 0. Whereas the range is the domain of this function, which is r. So the logarithm has range r, the set of real numbers, and has its domain x greater than 0. And this is why we have to take the limit when x tends to 0 plus. It also, here, it goes to minus infinity from this side here. Calculate the limit when x tends to 0 of 1 minus e to the minus x. When you see some cumbersome relation of this sort, you can do a substitution. You don't have to keep the variable. For example, if we do this substitution, then when x tends to 0 from the negative side, it means that x tends to infinity. Whereas when x tends to 0 from the positive side, then y tends to minus infinity. So you can apply, you can substitute minus 1 over x is equal to y, and you end up with the limit of 1 divided by 1 minus e to the y divided y tends to infinity. Now, when y tends to infinity, which is greater? Of course, e to the y, because this is negligible. And we know that e to the power e to the y, when y tends to infinity, is equal to infinity. So you end up with here we are finding the limit. It must be equal to 0. Whereas here, when y tends to minus infinity, e to the minus infinity, or the limit of e to the y when y tends to minus infinity is equal to 0, because it attenuates. So this becomes 0, and you have 1 over 1, so you have 1. Since the limit when x approaches 0 from the left-hand side is equal to 0, and from the right-hand side is equal to 1, so it means that the limit does not exist. And this is one necessary condition, that the limit exists when both tends to one precise real number L, then we say that the limit exists. Whereas if they tend to different values, then we say that the limit does not exist. Now, dominant functions. Functions, peculiarly, they have behaviors, they stick to behaviors, or they exhibit behaviors very much similar to personalities. When you have, for example, a person, your friend, and he's a dominant personality. He tells you, for example, let's go to the cinema, for example. Then you adhere to you respond to him by adhering to his demand. You said, all right, we go to cinema. And then if he changes his mind, no, we have to go to, and so see something. He said, all right. You always go with him, because he is a dominant. And same thing with functions. If you have, for example, functions of this sort, which of these are more dominant? Actually, e to the power x. E to the power x is the more dominant function among these three functions. So if you have, for example, a function, a compounded function between x to the n and e to the x, then the behavior of these two functions in the limit will follow the behavior of e to the power x. Whereas if you have, for example, x to the power n and logarithm x, of course, this is still stronger than this one. So the behavior will adhere, will comply, will follow the behavior of x to the power n. And to show this among these three functions, suppose, for example, we have x to the power n times e to the minus x. Which is stronger here? It's e to the minus x. So e to the minus x here, it's stronger. So when x tends to infinity, it follows this one. This one tends to 0 when x tends to infinity. So what you find here, x to the power n, still the limit becomes equal to 0. And same thing here. Logarithm divided by x to the power n. Here, which is stronger? This one or this one? No, x to the power n is stronger. When x tends to infinity, this becomes infinity. So wherever what we have here, still 1 over infinity is equal to 0. And again here, the limit of, for example, you have a numerator and a denominator. Actually, when you see e to the power x, you have to follow this one because you know that this is the strongest. So the limit again here, when x tends to the minus infinity, is the limit. It follows this the behavior of this function here, which goes to 0, and therefore the limit goes to 0. Now functions, and this is the final thing, we want to say that functions may have a limit at a point, but this limit is not equal to its value at that point. In other words, a function may have a limit, but the limit is not equal to the value of the function. And this we encounter, for example, like in this situation here. Here, the function has a limit. Why? Because it tends to 2 from the left-hand side and to 2 from the right-hand side at the point 1, and yet the value at the point 1 is equal to 4. So in which case, we say that the limit of the function, when x tends to 1 from the left-hand side is equal to 2, you substitute here x is equal to 1, and the rule when x is greater than 1 and approaches the 1 from the right-hand side, 1 plus 1 is equal to 2, so the function has a limit. But the value of the function itself is equal to 4. So here you have a peculiar situation. The function is defined at a point. So because we said before, the limit may exist and the function is not defined. But here both exist. The limit exists, and the function also has a definite value, but they are unequal, in which case we say that the function is not continuous, and in which case we have to follow a different approach to those kinds of functions. And this is actually the topic that we shall discuss further on. Now, this lecture, we have to conclude this lecture by saying that, first of all, there are two approaches to the subject of limit. One of them is to prove the existence of a limit. And this we saw in our last lecture when we used the pair epsilon delta, is called the epsilon delta mechanism of a German mathematician, by which he proved the existence of a limit. And to prove the existence of a limit, irrespective of whether the function is defined at a point, is to approach this point from the right-hand side and from the left-hand side without touching the point. In other words, you approach the point A at which you seek to determine the limit in a deleted neighborhood of the point A. If you find that the function f exists in a deleted neighborhood of a real definite value, capital L, then you say that the limit exists. If not, then you say that the limit does not exist. That if you wish to prove the existence of a limit. But if the problem is easier and you want to find the value of the limit of self, then you use a set of algebraic laws. For example, the limit of x squared, if you have proved already that the limit of x when x tends to a is equal to a, then the limit x squared, you multiply both together. In other words, you applied a set of algebraic rules to obtain the limit of function. And then also we discussed the number e, the definition of e from the limit, and we had a simple exercise showing how e appears in economics and in bank interests. So with this, we have come to the end of this talk or lecture about limits, and with this we have concluded the subject of limits, and from there on we study next time a new subject. Until we meet, I wish to remind you again that all these lectures are uploaded to the site of the Uniutunu Telematic University, and I wish you good luck until we meet. Thank you very much.